Hello everyone. Today I'm going to teach you how to use the formal definition of limits. As we discussed before, if a function fx has a limit L at the point x0, then it can be written as limit fx with x approaches to x0 equals L, which means the absolute value of fx minus L is arbitrarily close to 0, with x arbitrarily approaches to x0. Here, I just want to discuss a little bit why there is an absolute sign around fx minus L. As we know, if a function has a limit at point x0, then x can approach to x0 from either the right side or the left side, which will make fx minus L either positive or negative. For example, limit 1 divided by 1 minus x with x approaches to 2 equals minus 1. We can use a table method to illustrate this issue. As you can see, when x approaches to x0 from right side, x is always bigger than 2, although it can infinitesimally close to 2. Here is the corresponding function value. This is the difference between function value and limit L. As you can see, with x approaches to 2, the difference will approach to 0, but it will always be bigger than 0, so the difference fx minus L is a positive number. However, when x approaches to x0 from left side, x is always less than 2, although it can be infinitesimally close to 2, and the difference between fx minus L will approach to 0, but it will be always less than 0, so the difference is a negative number. So we can get fx minus L can be positive or negative. So we put an absolute sign around fx minus L. However, when we define fx minus L absolute value should be arbitrarily small or infinitesimally close to 0. But how close is the close? You can choose whatever you think is reasonable. So for the convenience, we should introduce a variable symbol epsilon to represent this infinitesimal positive number. Therefore, we introduce the formal or rigorous definition. For the function fx has a limit L at the point x0, which means limit fx with x approaches to x0 equals L. For all positive epsilon, there exists positive delta to make fx minus L absolute value less than epsilon if x minus x0 absolute value less than delta. Of course, it will be bigger than 0. So, as you can see from this statement, at first we should find the gap fx minus L. Then make this gap less than a variable symbol epsilon. This epsilon value you can choose whatever you want, but as long as you choose the epsilon, correspondingly the x value range should be determined in order to make fx minus L absolute value less than the epsilon. As we discussed before, x can approach to x0 from either right side or the left side, so x minus x0 could be infinitesimally small positive number or small negative number. So we should introduce the absolute sign around x minus x0. and make x minus x0 absolute value less than delta. Clearly, the delta should depend on epsilon. Here, I just want to give you some examples to help you understand this definition. For example, if we want to prove the limit 9x minus 5 with x approaches to 1 has a limit 4. So at first, we should find a gap, fx minus L, absolute value. Then we can get 9x minus 5 minus 4 absolute value equals 9x minus 9 absolute value equals 9 times x minus 1 absolute value. Because we are talking about x approaches to 1, which means x minus 1 should approach to 0. That's why we write this expression like 9 times x minus 1 absolute value. Then we want to make this gap less than any positive number epsilon. So we have 9 times x minus 1 absolute value less than epsilon. Or we can get x minus 1 absolute value less than epsilon divided by 9. In fact, x minus 1 absolute value is the x range. So we can assign delta equals epsilon divided by 9. Clearly, the delta depends on the epsilon value which you choose. For example, if we choose epsilon equals 0.009, then delta should be epsilon divided by 9 equals 0.009 divided by 9 equals 0.001, which means x minus 1 absolute value less than 0.001, or we can get x range between 0.999 and 1.001. However, if we choose epsilon to be 0.0009, correspondingly, we can get delta equals 0.0001, and the x range should be between 0.999 and one more 9 here, less than 1.0001. Here is the other example. If we want to prove 3 is not the limit of the function 9x minus 5 with x approaches to 1. At first, we just assume 3 is the limit of this function. Then we can follow previous procedures with the formal definition to prove the assumption. At first, we have to find the gap fx minus L, which means 9x minus 5 minus 3. The absolute value equals 9x minus 8 absolute value equals 9x minus 9 plus 1. Because we are talking about x approaches to 1, which means x minus 1 approaches to 0. That's why we write 9x minus 9, because it will become 9 times x minus 1. As we know, the absolute value of sum less than the sum of absolute value. So 9x minus 9 plus 1 can be written as less than 9x minus 9 absolute value plus 1. Then we should assign this gap less than positive number epsilon, which we can get 9 times x minus 1 absolute value plus 1 less than epsilon. So we can get 9 times x minus 1 absolute value less than epsilon minus 1. Then x minus 1 absolute value less than epsilon minus 1 divided by 9. As you know, in fact, x minus 1 is the delta range, so we can assign delta equals epsilon minus 1 divided by 9. Based on the definition, if the L is the function limit, then for all positive epsilon, the statement fx minus L absolute value less than epsilon should be true. So we can choose epsilon equals 0.05. Then we can get delta equals epsilon minus 1 divided by 9 equals 0.05 minus 1 divided by 9 equals minus 0.95 divided by 9, which is a negative number, which is contradictory to the statement that delta should be positive number. The 3 is not the limit for the function 9x minus 5 with x approaches to 1. This is all for today. Thank you for watching.